Thank you for attending our webinar here on floor safety guidance. And wanted to say safety is, we talk about the five S's in, sustain with lean and some Six Sigma initiatives, more with lean initiatives. And the sixth S that usually people bring in is safety. And our goal is to keep, and I'm sure your goal is the same, is to keep all of our workforce safe, meaning no injuries, because injuries can cost a heck of a lot in liability insurance, lost production time. No one wants to have anyone ever injured on the job for multiple reasons. So the hope is that there'll be a few takeaways from being with us today that you can implement to make your team or your lab a little bit safer. Morehouse, what we do, I see the list of people, most people know what we do, but we manufacture force calibration products. One's the Morehouse UCM. We have several that are available for year-end inventory. We provide force measuring equipment calibration services using international standards. And then these standards help us lower the uncertainties of customers' equipment. And then we enable customers to make better measurements, which helps make the world a safer place. That's really our purpose here, is just to create a safer world by helping companies improve their force and torque measurements. And a little bit of a double meaning today: create a safer world by helping companies improve their safety. So our force lab, we have 6 dead weight machines. Hopefully the 6 will be up and running. Right now we have 5 total, but we're building a 6600 as our 6th dead weight machine. Most of our dead weight machines are known to within 0.02% of applied force up to 120,000, and then we're making force measurements up to 10 meganewtons or 2.25 million at 0.01%. So a little bit of an overview. This is me. We had a metrologist mugshot social media campaign going. Really like this one, where it says, "I'm a metrologist. I solve problems you do not know you have in ways you cannot understand." It's something that I think we all can resonate with. In general industry, they do not understand measurement uncertainty. There are multiple large companies that do not have seasoned metrologists on staff. They make products, and we calibrate those products. And sometimes they make really good products, and sometimes they make really bad products because they do not have that metrologist on staff. So this webinar on force safety, it's really why we exist as a company. How do you start out as a company? What do you do? What happens to form that company? And in the 1920s, we were a machine shop. Just, Morehouse came into business in we were not in metrology or making instruments at all. However, there was this problem. And it's the late 19th and 20th century, boilers and steam engines were exploding. And by the 1920s, the problem was getting worse and the demand for these products was increasing. When a boiler blew up, the material was thrown all over like a huge bomb, and it often resulted in casualties. Ship plates were also a major concern. The plates were riveted together, and different materials could expand and contract at different rates, which would pop the rivets. I mean, you're on a ship in the 1920s, and rivets are popping and water's coming in. Not the greatest thing to happen, right? That could possibly happen. And it's even speculated that there was a fire on board the Titanic 5 days before the iceberg was hit that contributed to the weakening of the ship and its eventual sinking. Wouldn't that have been an interesting story or interesting chain of events, that the fire doesn't happen, and now the strength of the material is strong enough to withstand, maybe it still sinks, but strong enough to withstand that more people could have survived, or it could have sank slower, or someone could have rescued them. I don't know. All I know is that NIST did a really cool piece on the Titanic where they suspect that there was a fire on board and it weakened things. But the reason all of these things were happening is the material was not controlled and the testing methods were not good enough. And when we say testing methods were not good enough, we had these things, right? Brunel testing procedure. There's a 1921 Brunel hardness machine, and it was very difficult for these machines to be repeatable. And they needed an instrument to set, to test it, right? And it's the hardness of that material that drives everything that is built. In order to determine the strength of the material, they need to develop a test protocol to prove the material was strong enough to withstand the forces exerted upon it. They used what was called this Brunel tester. The Brunel tester used a 10mm ball and a hydraulic cylinder to push that ball against the material. The indentation of the 10mm ball was measured to determine the hardness. The main problem was that hydraulic cylinder to generate forces was described as inaccurate at best. So this drove us, Morehouse, and at that time the name of the company was Morehouse Machine Company, to work with the National Bureau of Standards, not NIST at that time, back in the 1920s, it was NBS, National Bureau of Standards, and create the greatest force measuring device by humans in 1925. That statement that people say the greatest instrument devised by humans is correct. It's something that we are proud of because there was nothing else available. So in the lack of nothing else available to really calibrate these machines, we can make that claim. Of course, today we can't make the claim in 2022. So my great-grandfather was instrumental in creating the Morehouse proving ring, and it was created to calibrate these Brunel hardness testers, which would help standardize the applied force and provide a method to more accurately measure the strength of material. And when we provided a method to more accurately measure the strength of material, the world started becoming a little safer because now the engineers could do the calculations, and they could know their calculations would be good on the boilers that were blowing up because they know the strength of material. So it all comes together. Safety comes from the minute we developed the Morehouse proving ring because there was a need. There was a need to keep people alive and know the strength of material. So, outcome for today, safety is the reason we exist. And the outcome today is participants will learn about unsafe loading conditions with several types of force instrumentation. And hopefully we'll provide some safer alternatives, including properly designed adapters. So let's look at this. Those that have had some classes with me know that I use some of these pictures. This is a more current one. This is an example where lower margins of safety existed, right? It's a crane. It's one of those big cranes that were falling. The wind would blow, and then this crane would break off, and then it would fall, and sometimes it would kill people. And several crane people, after closely examining the photos and videos, said they believe pins were removed early. And they say it's practice that has become common in the industry, a way to save time during disassembly, despite the safety risks that it brings. So you have these large cranes and you have pins that keep everything rigid and together to withstand some larger winds, and it's a real pain in the butt to keep these pins in and start dismantling the crane. So what they would do is they remove the pins early, winds would come, and the chance of occurrence, probability times impact, as we're looking at risk, the chance of occurrence was generally low until it wasn't. Right? And this is what happens in a lot of companies. It becomes complacency. Like, failures of things, right? People become complacent when they have long-term success, meaning long-term, large, maybe it's years, maybe it's weeks, where nothing happens. So people aren't taking the preventative action. And that could be something that's happening in your lab today. Hey, it hasn't happened in 10 years, but doesn't mean it's not going to happen tomorrow. So, question for everybody here. I'm going to show some pictures. And the main question is here, what load cell is damaged? Anyone want to take a guess? You have a load cell on the left, and then you have one on the right that has its top completely right deformed. So The answer is the one on the right. When something was an outie and became an innie, pretty much not going to work anymore. Here was an interesting one. The customer called us and they said, we don't understand this. Every time you do the calibration, it's out of tolerance. And our salesperson asked for some pictures. What we found out was that our force gauge, used here in this picture, compression force gauge, model 45C, was being used in a tension application. The threads are not designed to carry the forces in this application, which is unsafe, and the overall setup doesn't look too safe either to bolt something onto a forklift, pull on it. It's what people do, right? Until you know better, it's a problem, right? And then after you know, hopefully you correct it. Force calibration, here's tension, right? We were talking compression, tension. A compression is a push, tension is a pull or stretching. So that gauge was being pulled when actually it was designed as a push gauge. So talking about safety, one thing we really want to do when we're making force measurements, just for good force measurements, good repeatability, reproducibility, is we want to make sure everything is always aligned properly. This video here, picture, it's a video that's online, shows a Morehouse load cell. One picture you can see a line nice on the machine, nice vertical line of force, and then this on this side just not aligned well at all. So if I'm in a machine like a UCM, you can do this. Typically the bars will tip, but what you want to be aware of is if you have like a ball-on-ball loading condition or you had other loading conditions and the technician doesn't align everything, things can kick. And if things kick, things can fly. So that gets us into one of the do not load between unstable surfaces. Under load, the instrument could be ejected from the machine with tremendous force. Never use a setup where there are two spherical surfaces opposing another without making the appropriate adapters to contain the instrument. We have developed special adapters for this type of loading. Without the appropriate adapters, the instrument could be ejected from the machine with high force. That's what we're showing here. And sometimes you have such things as rocker load cells. Are really one good example of that. It's a load cell that's manufactured, quite a lot are manufactured with two spherical sides, and you need to contain it. And if you just put this in the machine, like I said, two sphericals, all it takes is the slightest bit of misalignment, and that could kick out of the machine. Something else. Do not load between unstable surfaces. Under load, the instrument could be ejected from the machine with tremendous force. Never use a setup where there are two spherical surfaces opposing another without making the appropriate adapters to contain the instrument, right? And now we have do not load between surfaces that exceed 1 degree deviation from parallel. That's really what we're saying here, that this is a dangerous situation. Load balls need to be made of hardened chrome alloy steel, and that it is recommended size to withstand the force applied. Never use a carbide ball. Carbide is brittle and will shatter upon load. And if you're using load balls, use a manufacturer that you can trust. I mean, we're not making load balls. We're buying them and reselling them. We had a batch of load balls that were supposed to withstand 200,000 pounds of force, and they all smashed at 98,000. If we didn't test it, would we have known? No, we would have shipped them to the customer. So be wary of people that are just buying parts and reselling them to you without the testing, because this part's $15. When it's tested, it's much more. It could even be less than 15, just depending. I'm cutting in purchase order, people factor, ordering, shipping, repacking, all of that fun stuff. But yeah, chrome. Never use chrome, alloy steel, and never use carbide. Also, find a company that you can trust what they're making and stick with them. Because there are some companies out there that will sell things that aren't suitable for what they're being used for, or there are people that will buy things and use them the wrong way. So we talked about some things about force safety and alignment and using the right adapters, but the other thing that we get asked a lot is, what do I do with old adapters? Right? Should I have them x-rayed? Should I have them tested? Should I visually inspect them? The answer is probably everything you want to do with them, though at some point they're so old that the service life of adapters could be nearing the end of it, and it might not be worth putting more money or more resources into all the testing and everything else as opposed to like buying something new. So there's several factors that go into this: design, number of load cycles, magnitude of each load. Better material manufacturing and quality control process provide more reliable strength values for design than 20 years ago. It's really probably 30 years ago. Our engineering team used Solid Modeling, SolidWorks. There's really good programs out there that you can look at the stress analysis of everything, and you can be more predictive in what your design is than, say, 1980s, 1990s, where it was all calculation and test. But even here, calculation and test, this is an old adapter that broke. It's ours. The source of the break was the machinist actually took a little bit too much of an undercut, and we did not have a 2-to-1 safety factor. So it failed a little bit early. And the top, it's a grade 8 bolt, and it failed, we were estimating, after about 350,000 load cycles. New adapters are designed for life cycle at least 500,000. And that's what we should have expected from this one. I mean, eventually it would have fatigued and broke. That's about 50,000 calibrations, and failure at close to 1 million load cycles. So that's something to consider. All that happened here was a little bit of undercut, and it shortened the life of it. We did not have the 2-to-1 safety factor. Therefore we didn't have the 1 million load cycles. Really easy to do if you don't have the quality inspection, or you do not over design your adapters a little bit. Now our engineering team is into a bit of over design because it's just not worth the risk of having things break early. Wrong tension adapters. If any of these look like a tension adapter in your calibration lab, there is a problem. Even straight threaded rod can introduce misalignment issues, as they can distort the line of force in non-Morehouse machines. Now, our UCMs, there's some other centering features that are in them. Deadweight machines sometimes have centering features depending on how you're loading it. And then any machine misalignment of 0.01 degrees can affect the reproducibility of some load cells. Even our spherical adapters can only overcome about 0.1 degree of misalignment. This is an interesting topic. It's a little bit off of safety, though it's who's right in that the design. Do we make the best force machine in the world that's plumb level square rigid so that any load cell or other instrument can be put in and have perfect repeatability, reproducibility? Or do we make a really, really good machine where we rely on the manufacturer of load cells to make sure that they're compensated for off-center loading and some misalignment built into it? I can tell you that to make machines where every piece of equipment would be perfect would not replicate end use and would cost an absolute fortune, as the amount of material, design, and everything else that goes into the machine would cost just exponentially increase the engineering, design, and everything else. And the market, at the end of the day, it does not replicate use. So that's what we're really fighting. And good load cells, if you buy the right load cell, the manufacturers will have compensation for like a little bit of misalignment, a little bit of off center, all this stuff. You buy the wrong load cell and the errors will be huge. So we start talking about adapters that can reduce some of these errors, and people have seen this one numerous times. But I'm also going to talk about safety on tension links this time through. But here, the right pin versus wrong pin, a difference of 860 pounds or 1.72% error on a device that's spec'd at 0.1% or plus or minus 50 pounds. You put the proper adapters in here, proper pin size, everything else, you get a much, much safer measurement. And then here's what we're looking at here with the proper pin size is the E shackle pin diameter, and our patented Clevis kit really we looked at all the manufacturer's data sheets and we came up with kits. So any of these walk in the lab, you have a Morehouse set in Clevis, you should be able to calibrate the device and do it safely. Versus someone made this, right? You see the welds? The lines, all of the lines, it does not look like full 90-degree angles. If we look at this in more detail here, over here, it looks like something, right, is starting to deform. And then we have this pin, a small pin in this large area is going to start wearing this part. And that's really what I'm showing here in that red area. So once this starts happening, it's only a matter of time before this happens. And I joke, this happened in our lab. We are not immune from any of these things that we're talking about today. We have people that sometimes think that they know what they're doing, and when they don't, bad things happen. What typically should happen is, at least for us, is the engineer gets consulted and said, hey, can we do this? And they run the calculations, but you should not put a smaller than the hole size pin in these clevises. And what eventually happened, like that one that I showed beforehand, that little bit of deformation and wear will eventually crack. Now I put a C-clamp on this because after it all happened, I told the engineering team that I said we had a slight accident, but don't worry, I already have it fixed, and that was just deflecting from something that should not have been done. But yes, there were root cause analysis and everything else, and it came down to technician assumed that they could load this with a smaller pin to 330,000 pounds of force, and they should not have. Now, that brings us to safety notes on this topic and the TMA Clevis setups. Ensure the Clevis pin is fully inserted. If the design includes safety pins, ensure they are installed before loading. Some tension link load cells are designed with non-cylindrical hole or a very large chamfers. This effectively reduces the contact area on the pin and will decrease the maximum load capacity of the pin. And then never use fixtures that don't have traceability back to their load ratings. Always remember the load ratings must be reduced if the setup does not match the original design intent. This is a big one, because this is where we failed on that other drawing, or in that other slide, right? It did not match. We used a smaller pin, it did not match, and there was a problem. So in addition to that, you can see some other things over here. Not centering the link in the clevis will affect accuracy and may overload the clevis. Verify pin sticks out both sides of the clevis. Most clevis max load ratings are based on the load cell width being close to the clevis opening. If the load cell is noticeably smaller, the operator should not proceed until they are sure the clevis is safe for the given setup. Yeah. And always use manufacturer's recommended pin diameter. Pins smaller than rec can cause load cell failure. For any calibration accuracy, pin diameter should match. And that's what we started with on the accuracy. So not only if you do not use the proper pin size are you going to be in large error that you could adjust and introduce and pass on huge bias to your unsuspecting customer, though your technicians and the people making the measurements could be at risk of the clevis breaking. And when that happens, objects could potentially fly and hurt them. Tension member assemblies. We've had people do this. We've had people do some of this, right? So this is easy. Use this. This is the proper setup, not this, or not this. The wrong setup here will most likely deform or even crack the adapters. That's actually what we had happen, that the adapter cracked. Use the wrong adapter and wrong setup, and it cracks. Luckily, when that happens, a lot of this stuff is contained. It's a replacement part. But when things break, if you're a technician or if you've ever been around it, I've been around too much of it in my lifetime, and we're non-destructive testing. But yeah, just material failing, it lets go, and when it lets go, there's an awfully big bang, and it will wake you up like nothing else. It's almost equivalent to one time I was unplugging an old radio, and I created the circuit on the plug as I was trying to yank it out from behind the couch. I grabbed the whole 120, and that pulsed through my entire body, and all my muscles started clamping on the outlet, and I had to take my hand and hit my arm off. That woke me up a good bit. This is about equivalent to being shocked with electricity when something goes. It will wake you up. Other safety notes: never manually lift any parts that are too heavy to control with 100% confidence. Proper material handling equipment includes lift carts, or material manipulators should be used. And then we have this YouTube video, how to set up a tension using our quick change, and how to set up in a UCM. But every TMA, tension member adapter, that's what TMA is, connection carries the full load unless otherwise stated. TMA components are to be fully tightened by hand and backed off about a quarter turn. That's what we're saying here. For connection directly to the load cell, and manufacturer's literature should be reviewed for additional guidance, and connections must be checked every time before starting the calibration. A little bit of a fun story here. We had a customer send in a load cell, one I've never seen before, where they said, hey, we want you to calibrate 100,000 pounds in tension and 100,000 pounds in compression. So we could do, okay, not a problem. Load cells rated, a stamp right directly on the load cell is 100,000 pounds. We hadn't loaded it before. We loaded in compression, no problem, goes to 100,000. Loaded in tension, and it breaks at 98,000 pounds. So our dead weights, the bolts, all the bolts in here that held that load cell together, these little bolts here, just sheared off. 98,000 pounds falling in about an inch creates a very loud bang in our dead weight machine. Enough to startle you, wake you up, and really question your occupation. So what happened? Why did that happen? When I investigated that load cell, and I wish I would have a picture here to discuss this, because a picture is worth 1,000 words, right? Going back to the manufacturer's data sheet, 100,000 pound tension was an optional, was something that was optional. You needed to tell that manufacturer that you wanted it, at which point they would use better bolts than what they used. The literature claimed that the bolts that they used were only good to 25,000 pounds in tension unless the optional tension upgrade was purchased. I had never in my life seen this, and I have never seen it again. It was just horrible, horrible manufacturing, because none of us knew it. And as things come into our laboratory, we're not inspecting the hardness of the bolts in the load cells. We are making the assumption that if the load cell has a stamp capacity of 100,000 pounds on it, that we can load it to 100,000 pounds. So be a little weary. It's never happened to us again. It was bad, and yes, we lost that customer because they were not happy. We were not happy. they were not happy. They claimed we broke their load cell, and we claimed you needed to really tell us that this was not rated for 100,000 pounds, even though all of the tags, serial numbers, and capacity stamped on it say 100,000 pounds. So, lesson learned. Common other some other errors. It's weights and handling. Stacking weights can have issues. Slow and dangerous. You could have ergonomic issues. A lot of people making torque measurement. Asking somebody to continually put 50 pounds on and off up to 2,000 pounds, 1,000 pounds all day long could be a problem. Other issues with weights is often not corrected for force. Corrections for force must include correcting for gravity, air density, material density. And let's look at this. Hopefully everybody can see it. It's one of my favorite videos because it's me stacking weights. But sometimes people make measurements like this, right? I say, hey, I'm exercising here, right? How do you center these weights? These are the weights I have on this small S-beam cell. And this is very contained. But what if it falls the other way, right? Instead of falling backwards, which I biased it the way I put the weights on for this video, but what if it falls forward and the weight falls on the floor and hits me in the foot, right? There's a chance that it could crack all the bones in my foot. Or there's a chance that it hits at an angle where it just does nothing, and now I just need to worry that that I damaged my weight, that it could be out of tolerance. So nothing ever good happens when things like this happen. So off-center loading issues. Most handheld force gauges require different centering fixtures for alignment. If the line of force is not pure, a large measurement should be expected. So yeah, if you're off-center, you're stacking things or doing things, you're not going to make the right measurement, and it can impact the safety. So we have these L bracket kits. The kits simplify setup, reduce errors with stacking weights, and they can be used on almost anything. Top block and hardness. The reason I talk about this is we started with the hardness of materials, but if we look at this, it's just two calibrations, right? One setup here on the right and one setup on the left. We're just these numbers are coming from the different hardness of the top adapter, and there's a radical change in the amount of deflection depending on the hardness. And we're going to get to why this could be a safety issue. There's a lot of things that can go wrong in here with top adapters. If engineers do not design and make the appropriate top adapter with the proper size, thickness, and we apply too much force, it will crack. And once it cracks, that creates a whole nother set of problems if things fly out. Typically, you'll get a stress crack, and it'll just make this horrible tinny sound, and it'll just break. There are times when if somebody keeps going, it will slide off and be flung out of a machine. So the initial break usually not as much of a problem as if somebody keeps going after they hear that horrible sound. Then it gets really unsafe really quickly. So what happens here? Top adapters, material with different hardness experience different amounts of lateral deflection under the same amount of load. Therefore, the varying hardness causes different amounts of stress between the block and the load cell. And then above, we're showing steel to steel. It gets much worse if we use softer material. What happens as far as safety is material with a lower yield strength than what is being applied will deform until the maximum compressive stress is below the material yield point. So right here, deformation until compressive stress is less than yield strength. And then all of a sudden we start to mark things. And when we start to mark things, we create unflat or unflat, unlevel potential loading surfaces. And if we continue to mark this, and we have things, loading surfaces that are not flat, then we go back. Eventually, we could be out of the slide that we said about any misalignment in the angle, and we could have a safety issue. We're going to have repeatability issues and bad measurements, but if we continue to deform and mark things, and eventually we might even get it to a point where the block cracks. So What we do with our material here in the hard block, these are over designed for the most part. They could be a little bit less height wise, uh, though we over design them intentionally. And the top block, a steep radius, concentrates the force over a smaller area and may cause the material to permanently deform. That is going to happen. Once you marry a top cap to the load cell, it's like anything else. It's married, it's there for life, hopefully. And if it deforms, that's fine. It'll deform with the load cell, and that deformation, we have really made these a bit of overkill as far as the design, so they do not break, or hopefully they do not break. Overloaded risk. So if I'm going to overload something, this is Young's modulus, and we get to yield strength here. So I take the load cell up, and the tech starts overloading it. It's probably still good in this region. I can still recover and use it. But once I start going on this curve here, I'm creating problems and I'm altering the material so it's not going to come back to its normal shape. But what the point of this is, when we get to this plastic region, like our grade 8 bolt, we've shortened, we have shortened the life cycle of our product here. And if we've done this with adapters or done it with something else, now that 500,000 to 1,000,000 life cycles could be half, could be 2/3. We just do not know unless we know the exact amount of plastic deformation. So be wary. If you overload something, it might need to be replaced. So mechanical tensiometer. The general method, if anybody's calibrating tensiometers, I know some people on this call are, they more than likely they have a beam, they're hanging the cable from a beam, and they have a pan, and someone manually stacks weights. Everything is out in the open. Sometimes even 2,000 pounds of weight is out in the open being stacked on a platform. And if that cable goes and somebody's lifting weights onto the platform, it's coming straight down. Often it's coming straight down at about 2 feet. I had, when we were weighing weights for one of our customers, we were out at for one of our dead weight machines, we were out at, we do some of the larger weights, we do not have the capability to machine. So we had large 8,000 pound weights, and our one vendor luckily can turn large diameter weights. And they were lifting things up with a load cell, and they used an I-beam, an I-bolt, and we were lifting it up, making the measurement. The eye bolt failed, and weight dropped maybe 8,000 pounds, dropped maybe 2-3 inches, and it dropped about an inch from my foot. So 2,000 pounds dropping from maybe 2-3 feet. If it hits somebody, it's going to likely going to sever their entire foot off. For me, if my foot would have been 2 inches over, I would have lost all my toes. It just, the guy beside me said he nearly, that Kmart commercial where I ship my pants, he said he nearly did that, but not shipping. Not good. And I said I could use a beer. Not good at all. General safety tips for calibration. Supervision of inexperienced employees is essential. Only employees with good mechanical and strong safety aptitude should use calibration equipment. So supervision, training. Marked. Only use fixtures that are marked or traceable to their rated capacity. There's a lot of stuff that's out there somebody had made that's not marked. They didn't mark the max capacity. Usually max capacity means what capacity gives me a 2x safety factor, so I do have room to overload it a little bit. I should not, though. Alone, never work on large machines alone. Condition, always check the condition. This should be everybody's habit. Always check the condition of the adapter, machine, and load cell. No damaged threads, no bent or distorted parts, no visible cracks. That's visual. It's the easiest thing somebody can do. If there are damaged threads, if there are visual cracks, replace it. Not even worth doing much of anything other than replace, because you're going to be in likely going to spend too much money on all the testing that's required, and it's just cheaper to buy a new one. And then safety factor. Never assume a fixture has a safety factor above its rated capacity. Dealing with being a manufacturer and dealing with several manufacturers, I cannot state this enough. Everybody seems to treat things differently. For us, it's a max capacity is a 2-to-1. Somebody else could have it at 1.6-to-1. Somebody could have it at 1.2. Somebody could have it at 4-to-1. It's all over the place. So UCM, if you're using a UCM, I know some people on this call are, do not overextend the jack ram. What are we saying here? It's this. This piece is the jack ram. It's meant to have about an inch of travel. There is not any safety protocol in this to stop you from overextending the RAM. We are working on that. We have built it for some. It's more expensive. Generally, we find that once people are trained, they do not want that additional safety. But if it's something that is a concern or you might have had frequent occurrence on, we do have options that can prevent that. Use only fixtures designed for use in the UCM. Never work on large machines alone. Always check alignment at low forces and verify everything is reading correctly. Never assume a fixture has a safety factor above its rated capacity. And then use the appropriate lifting mechanism to not hurt yourself. Ergonomic issues. And for your technicians, if you're not the technicians, providing the right equipment for lifting will keep your technicians safe. It stops from back pulls and everything else. I had to laugh the other day because Wayne Gretzky, who I'm a huge Wayne Gretzky fan, a huge hockey fan in general. I think Wayne Gretzky's a great person and whatnot. And he was friends with Gordie Howe, and he said how did Gordie Howe play hockey so long in life? Because Wayne Gretzky, I believe, said he doesn't really skate or play anymore. And Gordie Howe, Gordie, he played well. Well, he was the Tom Brady of hockey. He played well past his prime. In any case, Gordie Howe. The story was Gordie Howe told Wayne Gretzky, I go out on the ice and I skate and stuff like that. However, I don't do anything dumb like bend over to pick up something and bend over to pick up a parcel, I think is what Wayne Gretzky said. And it's kind of funny because these are the things not in our applications. Of course, we're probably all bending over to pick up a parcel, but if you look online, it's going to say squat. It's going to say bend your legs, don't overexert your back. But if we create conditions where people are can do whatever, bad things can happen. So, I mean, I personally hurt my shoulder just reaching for something, and it's been 13 months of pretty poor sleep. I wish I could go back and not reach for that thing. So we talked a lot about some safety. Hopefully there were some takeaways, and there's also all these other errors when it comes to force calibration. I like to sum them up in basically one sheet. I have this uncertainty budget here and just started to show some things to be aware of, different loading profiles, 10 volt versus 5 volt, different excitations, overshooting a test point. And you'll find blogs, or if you've had our training, the force training classes, we cover all of this and more, using a load cell and decreasing mode without having it calibrated there. Tension link pin size, we talked about that today. We talked about hardness today, different hardness and top adapters today. Shear web load cells, not using the adapter that was installed in them or trying to take it out and make a measurement. All of these things can impact the measurement result, and some of them can impact the safety as well. So, talking about keeping our technicians safe and us safe, we also should talk about keeping our equipment safe. And then here we have custom cut cases. And I laughed the other day. I was just talking to somebody about this. People see that we charge for these cases. At the end of the day, right, we're cutting foam, we're doing all this stuff, we're ordering the parts. There's hardly any money in these cases. However, they have been absolutely fantastic in reducing shipping damage. And when they reduce shipping damage, they also reduce our overall cost. As now things come in the case, we open it up, we calibrate them, they go back out. We very rarely, when somebody has a shipping case like this, very, very rarely have an oops moment where something's breaks, a cable, something's come loose, a box is cut open. We've had, in my experience, and since we've been doing this in 10 years, we've had two incidences, major incidences with these cases. And one was, I think it was UPX. Yeah, it was UPS. It was left on the conveyor belt where it kind of got jammed between the belt and something else. And the conveyor belt sanded a lot of, just destroyed the case, meaning it sanded a bunch of the plastic, that hard plastic off. The equipment was all okay, so that's probably not a major one. And the other one that was major was that someone dropped a pole, I believe, that pierced the case and broke one of these laptops. But overall, everybody that has these cases, besides them getting lost in a shipment, which can still happen, nothing really prevents our shipping carriers from losing things, especially around the holidays. Though it's just been fantastic. We don't have to call people, right? It comes in here, we calibrate it, it goes back. If we get in a damage scenario where we ship something back to you in a box, and something like this happens, like the bad here, it's a lot of time and energy on both parties to file a claim. That takes man hours, right? Or someone's time is burnt. Then they have to inspect it. They come out, the paperwork, everything else. It just does not make any sense. And then at the end of the day, a lot of times you don't get paid, right? Oh, someone else's fault. You didn't use the right pressure proof box. You didn't do this. You didn't do that. So highly recommend this for the sanity of everyone involved. Is these type of cases. Next best thing is double boxing everything. Very low occurrence of damage. The only downside of double boxing is you have to keep all these containers somewhere, and though you have to keep these containers, they make a very nice storage case to put things away when you're not using them. These double boxing, not so much. So hopefully that makes some sense. And then global concluder and decision, just talking about safety. If you don't trust your cal provider, I'm writing a new paper on bias. And if one level, like under reports uncertainty, or say this level right here, the accredited calibration provider, gives you an instrument, a 10,000 pound load cell, and they say you need to load it to 10,009 to generate 10,000 pounds, right? Or we say that. And then this supplier ends up just loading it to 10,000 and not 10,009, and they have, now they are -9 lbf, right? -9, and then they start making measurements. Every tier. So if you do something unsafe, use the wrong adapter, whatever you do, from the tier that happens, every subsequent measurement is probably no longer metrological traceable because the measurement uncertainty is not accounted for correctly. So that puts our whole process at risk, and then when this risk is propagated, we can expect really cannot work properly. So our download page has this number one force measurement, right? I'm going to share with everybody this. This is only for SEO, search engine optimization. I do not love it, but I'd rather, on a topic like this, I want this coming up in the search engines, right? We all want this. We want people to make safe measurements. So hopefully this group, hopefully there's been some good takeaways. If you have questions, please put them in the chat window. I can open up the discussion further. I do have an ask. It is the holiday season. I thank everybody for spending their time with us. But my ask is this. We are at 900 and some followers on YouTube. When we get to 1,000, we can control what video comes next instead of seeing an ad or whatever. You could see another video. So my ask is twofold: is to consider subscribing to our YouTube channel, and we publish a lot of videos uh, on things. This one is measurement confidence, accuracy versus uncertainty. A lot of metrology relevant videos. So I know everybody's lives are busy and they don't want to be marketed to and everything else. That's not what this is. It's just about following and spreading good metrological practices through this channel with videos, the recording of this webinar, and everything else. So please, if you would, consider subscribing to our YouTube channel. And then the other stuff here, you want more information, contact us, follow us on LinkedIn. We post things there all the time. We're trying to grow that subscriber network. And then remember, we have all these free downloads to help you. There's no sense in recreating the wheel if you don't have to. If we've already done it and you can use it, the spreadsheets, some of them are not protected to show all the formulas. Like I think the CMC sheet, take the formulas, make your own if you want to. It's just, if we can get you further faster, we're more than happy to help. So I wish everyone just a fantastic holiday, and I'm going to shut this recording and take some questions if there are any. So thank you for attending or watching.